Welcome to the first lecture in the Soft Earth Chalk Talk series. All of them have a somewhat enigmatic but maybe catchy title like this, Everything Flows. All of them also have a subtitle that goes in the liner notes or the title. This one of the subtitles is the squishy concept of a solid. Another subtitle is Everything Flows if you wait long enough. And on planet Earth, which is 4.5 billion years old, it can wait a long time. Right? Now, we're introducing you to this series, and I call it a lecture series, but it is not a course. Now, the reason I say it's not a course is if it were a course, I would bear some responsibility of transmitting to you accurate, technically rigorous ideas, statements, and this is not that. This is a very opinionated survey of a way of thinking about a bunch of problems. The other thing with a course is you have to do things outside of these lectures and you have to demonstrate some technical competence. And this is meant for us to be a break from coursework kind of thinking and to just think about a very informal, holistic thinking that we can do in a cartoony way, right? The other thing I'm going to warn you about, as you'll see, is that there will be equations that get introduced, but the equations will be almost like cartoons themselves. They're going to be math-ish. They're going to be one-dimensional. They're not going to be complicated. And I'm going to try to introduce them only in the way that we really need them in order to illustrate the concepts. So here's the thing. It's soft Earth, and we are connecting concepts in soft matter to concepts in geophysics. And pretty much everything in geophysics starts with plate tectonics. We can't get away from it. It's sort of the grand unifying theory of geophysics. It's also, I might argue, a huge and rare success story in having a truly integrated understanding of the physics of planet Earth. And we're interested in things going on at the surface of planet Earth, and that is ultimately driven by plate tectonics. So here is planet Earth, right? And we draw planet Earth. You might remember these cartoons. If you're a geoscientist, this is going to insult you, but if you haven't taken or looked at geoscience since elementary school, you probably still remember this sort of cutaway drawings of this onion of planet Earth. There's this middle part in here, the core. We don't care about the core, okay? Other people care about the core. It is not for us to worry about the core. The core is the iron center of planet Earth. It does very important things. It gives us a magnetic field. It's very generous for that reason. It sloshes around on the outside and is solid on the inside and does all kind of cool stuff, but it's not very relevant for us. The part we're more familiar with on the other end, right, is this part here, right? This is the crust. This is a thin shell, a veneer around planet Earth. It's the surface of our planet, and it's the crust, and it is crusty. It's brittle. It's a little shell. It cracks in places. This is the surface that we live on, and the vast proportion of the volume of planet Earth is this part in the middle, the part between the core and the crust, right? And this part here, which I'll label in green, is the mantle. Now, the thing about it, why we care about the mantle, is I'm drawing these little arrows here. Even if you're not a geoscientist, you may have heard that this mantle convects, right? So what do I mean by that? So the center of the Earth is very hot. The surface of the Earth is, for all intents and purposes, effectively 0 degrees Celsius. So there's like a order 1,000 degree difference in temperature between the center of the Earth and the crust, right? And so you can think of this mantle in the middle that it's getting heated from below. So I'll give little like terrible looking flamies. And it's getting cooled from above. So I'll draw a little snowflake up there. right? And so like a pot of water, it's heated from below, it's cooler on the top, the hot material comes up, it rises, it cools at the top, and then it sinks back down. So like a pot of water, it's convecting under this heat, but unlike a pot of water, it is convection of what we would consider to be a solid material. So there's this kind of paradox that's immediately introduced with this mantle, which is that on the one hand, this material is a solid. If you were to be able to magically reach down into the mantle, pluck a chunk of this rock out, keep it at the pressure and temperature conditions that it's in, deep down there in the mantle, and squeeze it, you and I would say this is a solid. If I were to hit it with a hammer, it would break apart. If I were to throw it at you, you would get injured, and everyone would say this is a solid material, right? So in some sense, it is mechanically a solid, and yet it is also behaving like a fluid, right? This is interesting to us. This is the sort of thing that we want to talk about when we say that everything flows, is the mantle is actually rock, and yet it is flowing. But it is worth talking about the timescale of this flow, right? So if you want to get an idea of a velocity of the mantle convection, it's on the order of centimeters per year. Okay? That's pretty slow. If you want to get a time scale from that, so the time that it would take for a chunk of mantle rock down here at the bottom to take the journey of a few thousand kilometers up to the crust, that time scale is millions to tens of millions of years. That's a very long time, right? If you then ask the question, okay, if it's behaving as a fluid, I can define a viscosity. And we'll get into how we define viscosity in a little bit today, right? But for now, we'll just say, sure, the mantle, if it convects, it's behaving as a fluid, it has some viscosity. And if I ask what is that viscosity, it depends on who you ask. It varies around planet Earth. But just give us a number, ballpark 10 to the 20 Pascal seconds. So that number might not mean a lot to you if you're not used to thinking about viscosity. But the viscosity of water is 10 to the minus 3 Pascal seconds. So the viscosity of the mantle is 23 orders of magnitude higher than water. It's like an Avogadro's number higher than water, right? Which is just to say, over human timescales, this thing does not flow. But over geologic timescales, the flow of the mantle is absolutely fundamental to the dynamics of planet Earth, right? So, okay, you get it, I get it, the mantle flows. Let's look at something now that some of you might be a little more familiar with, right? So I'm going to draw my bad perspective view. This is a valley with mountains, right? So this is a mountain range. This is a mountain range. And in between them, I'm going to draw a flowing glacier, all right? So maybe you've seen beautiful pictures of this. We're looking down from above, and here's a mountain. And there's a glacier that is streaming down this valley. And you see something interesting, which is that when the glacier gets to the end of the valley, when it becomes unconfined, you actually see the ice spread out. It's oozing, right? It's flowing. It looks like pancake batter, right? It's flowing between this valley. When it loses confinement, it spreads out. Of course, we all know that glaciers flow, even though if you stand and stare at the glacier, it doesn't move. When we look at satellite images, aerial photos, you just return to a glacier from year to year, you can see, of course, that the ice is flowing. So the time scale of ice flowing, let's just say order 10 to the 0 or years, right? If you come back year to year or you look at aerial photos of a glacier separated by a year, you can see noticeable deformation, okay? So the viscosity of ice, again, it varies, depends on who you ask, it's temperature dependent, varies across the planet, but let's just say 10 to the 12 Pascal seconds. So the time scale for it to flow is 8 orders of magnitude faster than the mantle. That's because the viscosity is 8 orders of magnitude less than the mantle, right? So it's the viscosity which is the measure of the internal resistance to flow that a material has, and that dictates this idea of how long we have to wait to see some noticeable kind of flow happen in the system. Now, not to be outdone, we can look at soil, and soil also does this, right? So we'll draw now a little hill slope perspective view like this. So I'm drawing this now because you're going to get used to seeing this drawing in other settings. So drawing a hillside, basically if you look at a hill, if you dig down deep enough, eventually you'll hit rock somewhere. But usually on top of that rock, there's a blanket of soil, right? And here, if you want to really get the idea, this is a hill slope. I'm going to draw some happy grass, right? Playful grass, right? So this is a hillside. And here's the thing. I don't know what it is. Glaciers got good PR. Everybody knows that glaciers flow. Soil is all around us. It's much more common for any of us to encounter soil than it is for us to encounter a glacier. And in fact, the time scale for soil to creep or flow is comparable to the speed of a glacier. Soil's everywhere. It's creeping all the time, and yet soil doesn't have good PR. Far fewer people know that soil is creeping relentlessly than people know that ice and glaciers creep and flow relentlessly. I don't know why that is. But here's the thing. Ice. Is it a solid or a liquid? It's a solid, right? I mean, by definition, when it's a liquid, we call it water. And when it's a solid, we call it ice, right? Soil. The sand grains and particles that make it up. What are they? Solid, okay, right? Yeah. So we understand that ice is a solid, that soil is a solid, and yet we say that they flow, right? And so there's this kind of contradiction with these earth materials that even these solid-like earth materials, we call them solids, but mechanically, they're flowing. And so what I want to bring up then is, as much as we might know that conceptually, if you poke at that a little bit, that apparent contradiction is not a shallow one. It's a deep one. In other words, underneath of that, knowing that it's like a solid, but it's also like a liquid, is some deeper questions about what makes things solid-like or fluid-like, and what about materials that are both solid and fluid-like. And it has to do with the definitions that we make about what is a solid and what is a fluid, right? So the typical definitions that we make, that everybody learns in grade school, in high school physics, in college, at ever increasing depth, ultimately is what I would call a thermodynamic point of view of solids, liquids, gases, of the phases of materials, right? And a thermodynamical view basically goes like this, right? So we draw a phase diagram right now. We're going to do it for water, for simplicity, right? And we know that there's pressure temperature regime where water behaves as a solid. There's another pressure temperature regime where water behaves as a liquid. And there's another one where water behaves as a gas, right? And just to remind you what's going on here, I've drawn this little molecular stick diagram, right? That we know that for water in a solid phase, what's going on is that the molecules have arranged themselves into this minimum energy configuration. Now, in this minimum energy configuration, the molecules are still jiggling, right? So the molecules can jiggle around, but in the solid phase, that jiggling is insufficient to overcome the bonds between the molecules. And so the molecules can jiggle a little bit, but that jiggling energy is less than the bonds that hold the molecules together. And so they arrange themselves in these nice ordered states, right? In the liquid state now, we have this configuration. So it's disordered, right? So in the liquid state, structurally, there is no order to the liquid state. And if you look at what's going on at the molecular scale, there's a lot more jiggling now, right? So there's sufficient energy to overcome these bonds that hold the grains in the crystalline state. But there's hydrogen bonding and other things going on between the molecules, so they slide past each other and they're breaking and reforming bonds all the time. They don't have enough energy to jump, though, right? So the molecules can slide past each other, but they can't jump away from each other. And so here is a higher energy state. And then, of course, if we keep increasing the temperature or change the pressure, we get to the gas state, which is also disordered. Of course, the molecules are further apart, and the energy and the fluctuations associated with that of the molecules is even bigger, right? So this is the thermodynamic condition. And in this view, everything that we've talked about, the mantle, ice in glaciers, soil, are all solids, right? So what we understand then is that the thermodynamic view of phases is incomplete. The thermodynamic view does not provide explanations to us about why solid materials behave in a fluid-like way, right? And so, of course, it begs the question then, what do we mean for something to be a fluid or fluid-like? What does it mean to flow if things that we call solids do it? And then that leads us to saying that we need another definition, and it's a definition about behavior rather than a definition about the thermodynamic state of the molecules, right? So what is that other view? Well, there are two other views we're going to go through today. All right? If you can handle it. I know, right? I got to step out of view and get an eraser. So the second view is what we'll call a mechanical view of materials, right? So let's think about the mechanical view of an idealized solid, right? So the easiest idealized solid to think of, let's think of a spring, right? So we'll draw a spring here. We'll characterize this spring with a length L. And then what we're going to do is put a brick on it, right? So we know if we put a brick on it, we've put some weight, we're loading the spring is going to deform, right? So we'll leave that there, and we'll put the brick on here, right? And so we'll say, okay, I've put on a brick which is applying some stress. And I'll define the stress by just saying that it's the weight of the brick divided by the area that's in contact with the spring, right? And then I will say that that brick and the stress associated with it has caused a deformation, right? And we will define that deformation as a strain. And the strain is defined by the change in the length of the spring, in this case it's compression, relative to the overall length, right? So this is a dimensionless quantity that just measures the relative amount of internal deformation that the spring undergoes because of this stress, right? So for perfectly elastic materials, we know that they follow Hooke's law, right? And Hooke's law just says that if I ask how much stress does it take to cause a given amount of strain or deformation, that for a perfectly elastic material, and the model system for this is a spring, that it's just a linear relation, right? And the slope of that thing is, well, if it's a spring, strictly, it's the spring constant or the stiffness. More generally, the slope of that thing we would call E, big E, an elastic modulus, right? So if we double the weight of the brick, then we double the amount of stress. So you could do a set of experiments where you increase the stress systematically and you measure the elastic response that comes from it. And for a purely elastic material, you get this simple linear relation. Okay. Now, of course, we know that real solids are not springs. And if we do such an experiment with a solid material that we care about on planet Earth, like a rock, you will see that there's a regime where the material responds elastically. But we know that if we stress it enough that it breaks, right? So a classic experiment that we might do is subject a piece of rock to what we call uniaxial compression, right? So we just put a chunk of rock between two plates and we squeeze it, right? So under this scenario, when we begin squeezing, you'll see this elastic-like response. But when you deform the rock enough, eventually we know that it starts to crack, right? And when those cracks grow sufficiently that they percolate across the rock flies apart, right? So when the rock flies apart, what happens here is that at the point where the rock flies apart, there's a catastrophic loss of rigidity and the stress drops, right? The resisting stress just goes away, falls apart, right? And so when that happens, we then say that there's a yield stress. There's a stress at which the rock falls to pieces. So this idea for real solids, that there's an elastic response up to some limit and then it breaks, is the simplest relevant description of the mechanical behavior of solids. And there are a bunch of solids that are described well enough by this kind of framework, okay? And just to give us an idea of relating the rock to the spring, that in this regime for the rock, where as you squeeze it, the response is linear, it is indeed elastic. So there's a regime with a rock where you can squeeze it and there's a resisting stress, and if you release the squeeze, that the rock rebounds, right? So this elastic regime is reversible. It's deformation that you can impose on the rock, and if you take the load away, the rock will recover. Once this happens, of course, cracking is irreversible. You know that if cracks form, if you take the stress away, the cracks don't go away, right? So this is a reversible regime, and then this is irreversibility. This is the onset of an irreversible change in the rock. Okay. So this is the idealized solid. Now, we've also brought up fluids. And so let's talk about the idealized mechanical description of a fluid. So the easiest way for us to do this is I'm gonna draw a little schematic that is meant to represent Newton's classic experiment, where the idea of fluid viscosity was laid out. Okay, so the idea is that imagine that we have a plate on the top that is mobile, and it's sitting against a plate on the bottom that is not. And imagine that we put a liquid between these two surfaces, okay? So this is a little, think of this as a little thin film of water, if you want. There's a plate on top, and what we're gonna do is slide the plate on the top, okay? So we're gonna apply some force to the top plate. The plate has some area to it, so we can define a stress. In this case, the stress that we're applying is a shear stress instead of a confining or normal stress. I will be very, very lazy in these lectures and just say, when I write stress, I mean stress, and I'll tell you if I mean it to be a normal stress or a shear stress or something else like that. There's not going to be any tensors or anything more complicated than that. So, you know, I just don't want to introduce more variable names than I need to, so you'll just have to deal with my imprecision. But if you don't like or care about math, then it won't bother you very much, right? So there's some shear stress now that I'm applying, trying to slide this plate. And it's just the force that I'm applying on the plate against, divided by the area. Sure. And then what happens in response, right, is that the top plate slides, right? So I'm applying a force, and then I can measure how fast does the plate respond and slide across the water surface when I push on it. Now, that sliding is happening because internally there's a velocity profile. So there's this idea, it's not strictly true, but it's true enough, that when dealing with fluids, when fluids come in contact with a surface, there's a no-slip condition, which means that the water that is in contact with the top surface gets dragged with the top surface plate. The water that is in contact with the bottom surface doesn't move at all because the bottom surface is not moving. And therefore, we know that there's a velocity difference between the top and the bottom. The velocity at the top is the fastest, the velocity at the bottom is 0, okay? So we have this velocity difference, and then we'll just say that there's a thickness of this material that we'll call L. So now what we can do is we've defined the stress. We can define the internal deformation as the strain rate of the material, okay? And the strain rate for us is going to be the velocity at the top minus the velocity at the bottom divided by the thickness of the film. And because the velocity at the bottom is 0, right? The strain rate here, which is a measure of the internal rate of deformation of the liquid between these two plates, is just the speed that the top plate flows divided by the thickness. And for the simplest fluids, what we now call Newtonian fluids, and common things that we deal with on Earth, like air and water, are Newtonian fluids. What you find is if you make a plot of stress against strain rate, is a linear relation, right? And so there's this idea now that if you plot stress against strain rate for Newtonian fluids, there is a linear relation between the two, and the coefficient of proportionality is fluid viscosity, okay? So this is what fluid viscosity is, right? It's a measure of the responsiveness of a fluid in terms of deformation rate to an imposed stress on the fluid. Now, the one thing you'll notice about this is it says that, you think of shear rate is internal deformation. It says that a Newtonian fluid flows at any stress, right? As long as sigma is not 0, any infinitesimal amount above 0, it is going to flow, right? So a Newtonian fluid is always flowing unless the stress is 0, all right? And this is the simplest kind of relationship you can have. The other thing I want you to know is that in a Newtonian fluid, all deformation is irreversible, right? If you apply a stress on a fluid and you make it deform and then you take the stress away, it does not go back, right? So there's no spring-like behavior for a fluid, right? So you'll notice that in the idealized description of a solid and a fluid, they're similar, that we have this linear behavior. Now, one thing you'll notice is that for a solid, we plot the stress as a function of strain, the total deformation. And you'll notice that for the case of a fluid, we plot the stress as a function of strain rate, the rate at which the material internally deforms. Why, in the case of a solid, do we plot it in terms of strain? And in a fluid, we plot it in terms of strain rate? The answer is pretty subtle. I'm not going to answer it right now. We're going to answer it in about 5 or 10 minutes, right? But I'm just trying to plant a seed that even this idealized description reveals a kind of dichotomy, right? That if you choose that it's a solid, you describe stress against strain. And if you choose that it's a fluid, you look at how the stress changes as a function of strain rate. All right. Now, let's think about a way that we could break these two frameworks, right? I wouldn't be presenting these idealized things in solid and fluid if I wasn't going to tell you that they don't work for most things that we care about, okay? It's not very hard to come up with a material that confounds us or that breaks these frameworks, right? So one example, that I'll draw here is toothpaste. You can tell that's a toothbrush, right? A little toothpaste on top. So thing about toothpaste is that you put it on your toothbrush and it doesn't flow, right? That's by design, right? We don't want it to flow when it's on your toothbrush, right? You want something that you can put in your toothbrush and it's going to stay there. But what you know is that when you squeeze the tube, the toothbrush flows out, and when you stop squeezing it, it doesn't flow anymore, right? You know that you can't put a blob of water on top of your toothbrush like that and have it stay there, right? So there's something about this toothpaste that when you squeeze it, it behaves like a fluid, but when you stop squeezing it, it behaves like a solid. And that's by design. We want it to be a solid on the toothbrush so we can take it and apply it to our teeth. And then once we start brushing our teeth with it, it becomes a fluid again, right? So toothpaste is not the only material that does that. I don't have brown chalk, so I'll just draw this way. I know this looks kind of nasty, but let's just say that another thing that does this is mud. Okay, this is like a little blob of mud. It's got some fine particles in it and clay, and it's got water mixed into it. Okay, that's why the blue is in there. And what both of these materials have in common is that if you don't apply any external stress to them, they behave as a solid. Not just that, if you poke on them, but just a little bit, they're still also a solid. So both of them have some regime of elastic-like behavior, that if you poke them gently and you remove the stress, you can deform them and then they will return to where they were before, right? Hair gel is another example, and you can do this if you take hair gel and put it in your hand. If you poke it gently and then release, you can actually see the hair gel come back like a spring, right? So you poke a little and it's elastic response. If you poke a lot, you get an irreversible deformation or a permanent kind of response, right? So they have a regime of irreversibility and reversibility. If you really deform them a lot, they can eventually fall apart. Some of them might fall apart gradually. Some of them might actually crack. This class of materials we will colloquially call soft. So this is the first introduction of the word soft in the Soft Earth Chalk Talk series, right? And here, we're using soft in an intentionally general or vague way. The way that we're using it is that these are materials that live in some liminal state between solid and fluid, that they don't fit neatly into the category of solid or fluid. That is not the only definition of soft. And as we move forth in the Chalk Talk series, we will introduce and use the term soft in other ways that we define as we go. But for now, I want you to think of these materials as being soft. Another example is just sand. Sand is an example of a soft material. And for us, we'll say that going beyond saying that they're just somewhere between solid and fluid, it's that they exhibit solid-like behavior under some regimes or stresses, and they exhibit fluid-like behavior under other regimes or stresses, okay? So if we look at where these materials will lie in the solid-like plot or in the fluid-like plot, we can do this. We can do this with mud, or we can do it with toothpaste, right? So if we plot it in the solid-like way, for toothpaste or mud, we would see something that is like this. So in this initial regime of a little bit of deformation, there still is an elastic-like response. But if we deform them too much, they start to depart from this linear response. And when they depart from this linear response, they enter this regime where the line is curved. And this regime is a regime that we will call plastic. Plastic can mean different things to different people, but to us, it's the deviation from an elastic response, which means it's both the deviation from this linear regime, and it also means that in this regime, we're now starting to undergo irreversible deformation. That if we were to remove the stress, it would not recover its initial shape, but it has still not fallen to pieces. You'll notice in the way that I've drawn this, that there is still a peak stress beyond which the material loses competence. So we can still define a yield stress for this material. But we'll even notice that when we go beyond the yield stress for something soft and squishy, that the stress drops but gently and not catastrophically. And so this idealized response of linear all the way up to breaking and then catastrophically falling apart is what we call brittle. And so when you hear the term brittle in a colloquial sense, you kind of think of things that fall apart easily. But brittle materials in a mechanical sense can be plenty strong. But what it means to us is that they have an elastic-like response, they get loaded up with stress, but then they take it and take it and take it until all of a sudden they can't, and when they fall apart catastrophically. This regime over here this is what we call a ductile behavior, right? And ductile for us means that these materials deform gradually under stress. And one way to think about it is that their failure envelope is very wide. So on the one hand, a ductile material will typically start deforming permanently and changing at lower stresses than a brittle material, which can be bad for you if you care about material strength. But on the other hand, the fact that these materials don't fall apart catastrophically, but that they deform gradually is good if you're worried about catastrophic failure, right? And so ductile materials just have that different mechanical response. Now, how about if we think about the same material, toothpaste or mud, but we want to put it in this fluid-like way of thinking about things? So what it looks like is this. It would say that there is a regime, this we'll call the elastic regime, that there is a range of stresses over which there is no deformation. Or alternatively, if you want to deform the material at a given rate, when you start trying to deform the material, it doesn't deform at all, and it just builds up stress until you exceed some critical amount of stress, and then it begins to flow. So the expression of a yield stress right here is that there's a critical stress at which you need to start deforming, right? Now, beyond that, what will happen is that there's this nonlinear regime here, and this nonlinear regime corresponds to the plastic part, right? And then, beyond that nonlinear regime, you have this again, a straight line which we call the viscous regime, right? And you'll notice that the straight line is parallel to the straight line for a Newtonian fluid. And so for this non-Newtonian fluid, if you want to think of it in a fluid way, like toothpaste, there's an elastic regime where there's no permanent deformation. There's a plastic regime over a higher rate of shear rates. And then eventually you get to a point where it flows and behaves like water, except it's more viscous than water, right? And so that's how it looks, right? And so you can take the same material and plot it in these two different ways. And you can either say that it behaves as a ductile solid, or you can say that it behaves as a non-Newtonian yield stress fluid. Both of those things are true. But which one do you choose, right? Why do we have this thing about plotting at a strain or plotting at a strain rate, right? And implied in this is that there's some time scale of deformation of these materials. So I'll give you a hint right now. We know that we can take a rock and we can stick it between two plates, and we can take our sweet time doing it. The rock isn't going to go anywhere, right? We can put it between these plates, we can mount it, we can come back tomorrow and start an experiment. We can stop the experiment, we can go home, we can come back and start the experiment again. What I mean is we know the rock is not flowing, right? On the timescales that we're worried about, this rock is not going anywhere. You know that you cannot do this with a fluid, right? If you try to put water between these two plates, the water's going to flow away immediately, right? Remember, Newtonian fluids flow at any stress, right? And so what's happening here is that the rock deforms so slowly, and in fact, the rock does not deform unless we apply a significant stress to overcome all these bonds that are holding the molecules together, right? What we know is that something like water flows under any stress at all. And so we can't put water inside of a piece of equipment like this and have it stay where we put it if there's any stress at all, right? And so it's giving you this idea that there's some internal time scale at which the molecules or particles or whatever in these materials respond to a stress. For a rock, that time scale is very long. And in fact, it's so long that we don't need to worry about it for our experiments. For water, that time scale is so short that we have to measure the response of water and how it changes as a function of how fast we push on it. All right? If that doesn't make sense, hopefully it will make sense with where I go next. Because what we need to do is introduce the third and last way to think about these phases, right? So we have the thermodynamic description, we have this idealized and then not so idealized mechanical description. And the third description is what I'm going to call a dynamical description. And by dynamical for us, I mean we're talking about time and changes in time. So to give you an idea about this, let's think about maybe an obvious and trivial example. Okay. But we're going to build our intuition from here. So let's say that we have a tub of water and we have a brick. And we're going to hold the brick on top of the water. And then at time 0, we're going to release the brick, right? So at some time later, we release the brick. Water splashes up in all directions, right? And we do something like plot the position of the brick as a function of time, right? And for us, we're going to say something very simple. We're going to say, you know what? The time scale that we're interested in is the time that it takes the brick to fall one body length and become completely submerged. And at that point, we'll say that that is the time scale of relaxation of the brick in the water, right? So we're going to define a characteristic time scale of relaxation. So in this situation, we know that it's very fast, right? So water gets out of the way pretty quickly. The brick is pretty heavy. It falls through. And we're just, again, we're defining this characteristic relaxation time. And just to give us a scale, we're arbitrarily saying the time that it takes for the brick to move one body length. Now, this is the beginning of the series. I need to warn you. When I say characteristic time scale or characteristic length scale or anything characteristic, you should be cautious. On the physics side of things, when we say characteristic, we mean a vague sense of what to expect and don't push us too hard, right? So does characteristic timescale mean the average timescale? Not in a formal sense. Does characteristic timescale mean some deterministically precise thing I could derive from first principles? No. When we say characteristic timescale, we usually mean order of magnitude. We usually mean ballpark, and it means something you could come at from dimensional analysis or scale analysis. So it's an intentionally vague term that is meant to give us an idea of a size or duration of something before we've done any hard work of figuring it out, right? So, the characteristic time scale for the brick to fall is very, very short. Of course, this is also length scale dependent. If you pushed on water and you said, how long does it take for a water molecule to get out of the way of another water molecule? That's like 10 to the minus 12 seconds, like a femtosecond, right? If you ask this on the time scale of the brick, it's going to be a fraction of a second, right? Maybe 100th of a second. I didn't do any calculation and we can figure this out, right? But it's going to be some fraction of a second, right? But we understand that it's very, very short, right? Okay, so that's the trivial example. Now I'll do another trivial example, right? Let's do an example now we're just going to put our brick on a table, okay? We're going to plot position as a function of time. It's a very boring plot, right? We would be surprised if the brick went anywhere, right? When no other force acting on it, we think the table's pretty solid. The table isn't going to give way to the brick, right? So from this perspective, the brick is just sitting there, right? Then from the perspective of a relaxation time, we would say that it's infinite. In the case of this relaxation time, of course, it's not 0, but we're going to say that it's something very small, closer to 0, right? So the relaxation time here for the water is almost nothing. The relaxation time here for the table is essentially infinite, right? And so those two are sort of obvious end member cases, right? So now let's think about a third case. So let's take our brick and place it on top of a nice layer of memory foam. Hopefully you guys have had the experience of memory foam. I have a camping mat. It's memory foam. It's great. It's even better than my mattress at home, right? So we're going to place this brick on top of some memory foam, right? So we know that this is something that's squishy, but we know that that squishy response is slow, right? If you make the foam too soft, it doesn't pad you very much at all. And if you make it too stiff, it feels like you're laying on a table. And so we like to make it something in between. And making that in between has a dynamical consequence, which is that, you lay on it and then you slowly feel yourself sinking into it, right? Until it finds some steady state. So if you were to plot position against time for the memory foam, you would have some intermediate relaxation timescale. It's not negligible, like 0. It's not anywhere near infinite. Maybe this is tens of seconds to a minute, something like that, right? And so you would see the brick relaxing. It would be fast at first, and it would slow down with time and maybe asymptotically go to 0, right? So there's this relaxation. So are you ready for our first dimensionless number of the Chalk Talk series?
Yes.
All right, let's do it, right? Okay. So to introduce this dimensionless number, we're going to do something that I don't usually do. We're going to get a little biblical. And this dimensionless number that we're going to introduce is called the deborah number. And apparently, I'm not a reader of the Old Testament myself, but the scientist that proposed this dimensionless number, quoted some old quote from the Old Testament that said, translated, of course, something like, "The mountains flowed before the Lord." The idea behind that is that something that seems so permanent and solid to us mere mortals, living here for the brief snapshot in time that we have on Earth, that actually under the longer timescales of God or nature or whatever your belief now, are flowing, right? And whether that statement in the Old Testament was meant literally that at that time humans had an understanding that even mountains actually literally flow, or whether it was just meant to be some symbolic thing about transience, I don't know. But it's rather prescient, right? Because we now know actually that mountains, even made of solid rock, do flow. Only they do so over what I would say geologic time. So I'll replace before the Lord with geologic time. No offense to anybody religious, And the deborah number is meant then to be a number that characterizes the degree to which things relax or flow compared to some timescale over which we care about, right? And so there are a few different ways to define the deborah number. I'm going to choose one that works for our purposes, and it goes like this. So for us, for my purposes, I'm going to define the deborah number as a timescale of relaxation, internal relaxation of the material, compared to a timescale that we load the material at. Okay, so I need to define those two things a little bit. The internal relaxation timescale, you can think of, at least conceptually, the way that I've laid things out here, right? For liquid water, the internal relaxation timescale is going to be directly related to the viscosity of water, right? So one way to think about this internal relaxation timescale is when I apply a stress, any stress, how quickly do the constituent particles move and respond to that applied stress, right? So we understand that for a very low viscosity material, that one way to look at it is it responds very quickly to an applied stress. And for a high viscosity material, it responds very slowly to an applied stress, right? For other materials that are not Newtonian, it becomes a little bit more complicated to anticipate what the internal relaxation timescale is. But we're going to say that this T relax is roughly a material property. That may not always strictly be true, but we're going to say that based on the material we're dealing with, there's some internal rate of relaxation or rearrangement of the constituents when we apply a load to it. That's related to the material, not related to the outside world. And the loading is going to be what we call like a boundary condition. What I mean is that we have a material, the material has some intrinsic rate at which it relaxes, and then we apply a stress or a load on that material from outside, right? And so we can define that by some characteristic scale. Now, also, I am fond of saying that one person's boundary condition is another person's model. What I mean is that for us, we're going to say that the loading comes from outside, from the Lord or whoever, right? The loading is imposed on our material, and we're just going to come up with a number. But of course, that loading itself is a physical process that someone else might be interested in, okay? So the loading time, though, in our experiment is something that we can prescribe. So I'll give you an example to make this concrete, or to make it rock. So let's think about a rock. And for simplicity, we'll put this piece of rock up against the wall. And we're just going to push on it now from one side, okay? So we're going to deform this rock by just applying a load on one side of it. And so we'll apply that load by pushing on it at a given velocity or a rate, u load, okay? That rock has a characteristic length scale to it here, right? And so in this situation, I would define T load, or the loading timescale, as simply, it's the inverse of the shear rate, or the inverse of the rate of deformation. In this case, we're imposing that rate of deformation, which for our problem is L over U, okay? So this is, you can think of it, this is a characteristic timescale that I am applying a load, right? If you think of it, I'm pushing on this rock, and this timescale is the timescale for the rock to deform. It's a characteristic timescale for the rock to undergo some significant deformation. And what I know is that rocks respond very, very slowly. Without knowing what the relaxation timescale of a rock is exactly, I still know that when I impose an experiment and I start squeezing the rock, that the molecules are not able to move out of the way, right? So when I squeeze the rock, the reason it behaves in an elastic-like way is because the molecules have some ability to move away from each other, but it's very, very slow. And my timescale of loading in the lab is essentially always faster than the timescale that the molecules can get out of the way, which means that I'm stretching their bonds until they break, right? And so in this situation, I would say from a dynamical point of view, for our experiment, that the rock is a pure solid, right? It's a pure solid, and the deborah number is much, much greater than 1. This relaxation timescale is something really big. Whatever it is, it's longer than the rate that we load the rock in the lab. And this is why the rock behaves as a solid when we play with it. It's because its relaxation timescale is really, really long compared to any rate at which we load the thing, right? Okay. So if we think about now like this situation with our water between the plates, we still have the situation where T load is 1 over the shear rate, right? So we dictate in our experiment how fast or slow we load it. And what we said is that the relaxation timescale for water is tiny. Whatever experimental rate that we're loading it at, we are not loading it at femtosecond timescales, right? We can't do that in an experiment. We can't shear it that fast, which means that when we're considering something like water, no matter the loading rate, it's always going to be slower than the relaxation timescale of water. Water is always going to essentially instantaneously get out of the way, no matter how fast we load it. And so in this situation, we call it a pure fluid, right? And for a pure fluid, the deborah number is much less than 1. So now, if we think about our memory foam, instead of thinking in terms of absolute timescale, now in terms of the deborah number, it's somewhere in between, right? We're not in the regime where it's pure solid, that as long as we wait, we don't see it doing anything. We're not in the regime where it's pure fluid, where it deforms instantaneously. We're somewhere in the middle. And so for the memory foam, I might say that the deborah number is order 1, okay? So the loading time and the response time are comparable to each other, okay? This regime, where the deborah number is order 1, is another way for us to define soft. It's a dynamical way for us to define soft, right? So we are loading the material and it is deforming and responding continuously. It's not running away from us as we load it, but it's also not standing there and resisting completely either, right? And that one is a useful one. So how about for some, earth materials that we might care about, right? I mean, I'm sort of making up numbers at this point. I haven't given you any real numbers. And I've told you that the loading rate is something that we can control, or that nature can control. But what about this relaxation time? I can't give you an exhaustive definition that works for everything, but I can give us a few examples. So if we think about mud, okay, so mud, if we wanted to find a characteristic timescale for mud to relax, one way to do it is to ask, what is the overall viscosity of mud when it is behaving like a fluid? So when we shear the hell out of it, it eventually reaches that Newtonian state where it's flowing. And we'll say that that's its viscosity. We also know that it takes some minimum amount of applied stress before the mud starts to behave like a fluid in the first place. And so a crude way to come up with a characteristic relaxation timescale of mud is just to compare the viscosity of mud when it's flowing to the stress that it takes to get mud flowing in the first place. Okay? Now, let's just think about a situation of a granular suspension. What does that mean? I'll tell you in a second. So a granular suspension, we'll just talk about particles that are in water, okay? So think about sand in water, for example. Okay. So in this situation, one characteristic timescale you can come up with, a simple one, is, okay, if a particle, grain of sand, wants to move in this suspension, it has to push water out of the way, right? So there is a viscosity of water that matters. And if you think of it, the force that the particle has to push that water out of the way is essentially the weight of the particle, right? So you can think that one way to come up with a time scale of these sand grains in water, if the sand grains want to deform inside of the water, they have to push the fluid out of the way. And you could say then that a characteristic time scale of relaxation, or an ability for those grains to deform inside of water, is related to the viscosity of water divided by the particle pressure, the stress associated with the weight of the particle, okay? And these timescales will be on the timescales of seconds for mud and sand suspensions and things like that, okay? So we understand now with these timescales how these are intrinsic properties of the material itself. And then the rate at which mud or granular suspensions are loaded is determined by us in our experiments or by nature, right? And that because of that, then, we can load it at timescales that are larger or smaller than these internal material relaxation timescales, and we can elicit solid or fluid-like responses from these materials. So, are you ready for it to all come together? Are you ready to have your minds blown by the synergistic unification that's about to happen? You were born ready. I love it. Okay. You ready? This is going to require us to erase the whole board. I know. I didn't want to tell you about this in the beginning. I should say, I didn't say this in the beginning of the lecture. In my lectures, I don't tell you what I'm going to tell you about, right? In a lecture, a scientific talk, typically for a course, you would do that. I like to tell stories, right? So I like to start, and you don't know where I'm going. And we're going to try to, not only in this lecture, but in a lot of the lectures, it's going to be like a nonlinear storyline, you know, in a movie. You know, that happens. It's experimental, right? And the nonlinear timeline, but after you see the whole thing, you piece it together. And you're like, oh, that thing with the rocks there was related to this thing he said in the beginning. Now I get it, right? So, yes. So, what I want to talk about is that this deborah number idea suggests that the exact same material loaded in a similar way can elicit different mechanical responses depending on the scale that you look at it, okay? I don't expect that to make sense yet, but let's now make sense of it with an example. So let's consider rock. And I'm just going to impose a few things for simplicity, okay? I'm going to declare that I'm going to imagine a world that is made of one kind of rock, all right? My world doesn't have different kinds of rocks at different depths. It's just one rock, okay? And I'm going to fix the relaxation timescale of this universal rock, okay? So let's just say that it's got a relaxation timescale of 10 to the 5 years, all right? That's a long time, but it's not infinite, right? It's a reasonable time for internal deformation of rocks. Now, let's also say that that rock is getting loaded at a given rate. Remember the timescale of mantle convection? That's also the timescale. Mantle convection drives plate tectonics, so that's also roughly the timescale that plates move around on planet Earth, right? So we're just going to imagine a planet of uniform rock with a uniform internal relaxation time, all being driven up, down, sideways at the same rate. we're going to say that that rate is order centimeters per year. All right? Now, if we consider a chunk of rock, we'll say outcrop scale, room size scale, right? A rock outcrop you would walk up to order 10 meters, something like that, right? And if you've ever walked up to a rock outcrop, the one thing you notice is it typically has a bunch of cracks in it. We'll get to that in Chalk Talk 3, right? So it has a bunch of cracks in it. So in this case, if we imagine the rock at order 10 meter scale, right? Remember, it's being loaded at this fixed velocity, the same velocity that our rock is getting loaded at everywhere on planet Earth. So this rock is getting squeezed or sheared or something else at order 10 to the minus 2 meters per year. And if we were to ask then, what is the loading time of this rock, right? Well, we know that the loading time is the length over the loading rate, right? And in our case, if we plug in the numbers, we come up with a loading time of 10 to the 3 years. So if we're loading this rock at centimeters per year, in order, the time it takes to see appreciable deformation is something like 1,000 years. Now that's long compared to us, but it's not much time before the Lord or planet Earth, right? And so, and indeed, if you were to ask, what do we get then in terms of the deborah number, right? So we have this relaxation time, 10 to the 5 years. We have this loading time, 10 to the 3 years, right? And what you're going to come up with is a deborah number that's like 10 to the 2, much greater than 1. So what it says is when I consider a rock at the scale of an outcrop, that rock is in the pure solid regime. So it's going to elicit a solid-like response. It's going to crack when it gets loaded. Okay. But we know that that rock does not exist in isolation. Sorry, I've drawn my little arrows the wrong way. We know that that rock is living inside of a mountain. So I'm drawing a mountain from the side. If you're a geoscientist, you know this, but if you're not, you might not know that if you could look into the heart of a mountain, what you often see is that the rocks are folded, right? The time scale, or the length scale of this, right? So let's consider what length scale we're talking about. Let's just say order kilometer scale, right? So it is very common for us to see on the length scale of order kilometers that rock is bent and folded, okay? And this little chunk of outcrop that we see over here is embedded inside of a mountain. That mountain is also being loaded, right? And if we ask, well, what's the characteristic loading time or the time it takes to cause some reasonable amount of deformation of rock at the scale of kilometers rather than the scale of meters, right? What we come up with is a time scale of loading that's about 10 to the 5, right? So what we come up with is a deborah number that is order 1. So it's saying that the same rock loaded at the same velocity will elicit a solid-like response at the scale of meters to tens of meters, but it's going to be floppy and soft and fold and stuff at the scale of kilometers, right? And of course, that mountain is embedded here on planet Earth, right? It's just one little mountain hanging out right there, right? And if we ask about the time scale of loading for the Earth's mantle, remember, here's the core, here's the mantle doing its thing. The length scale that we have here is more like thousands of kilometers, millions of meters, right? Let's say the same rock is still being loaded at the same speed with the same relaxation time, but the time scale of loading that we come up with now is more like 10 to the 8 years, right? Which means that the deborah number that we come up with is much, much less than 1, right? Which means that there's going to be a fluid-like response at this scale. This, I think, is a very simple but remarkable result. It says if I had the same damn rock deforming at the same damn rate, that it's going to break at small scales, it is going to bend at intermediate scales, and it is going to flow at large scales. And all of them are happening simultaneously, right? So the rock on planet Earth is flowing before the Lord, but it's only doing it at large enough scales. It's actually cracking and breaking before us at smaller scales, right? And what you realize then, right, is that this dynamical definition is a third dimension, right? It's sort of like the thermodynamic definition of phases matters, but that's like a one-dimensional view that doesn't give us everything. The mechanical definition matters in terms of thinking about how materials respond, but you can't really predict why they're going to be in the solid-like or the liquid-like. This one like adds a third dimension that makes the view complete, right? That allows us then to understand how we have different mechanical behaviors at different scales. Now it does, we're going to round this out with like one last problem and maybe, one last paradox to resolve. So we'll draw a line in there and we'll come back to our hill slope, right? So we're going to come back to our soil-mantled hillside, right? And if we do our deborah number argument that I'm not going to write out here, but it won't surprise you to find out that we already talked about soil flows. If you plug in our characteristic relaxation and loading times, you have to make some guesses and stuff, but you come up with a deborah number that is orders of magnitude less than 1. So what we know is that soil that's just sitting there, being loaded by gravity, it is flowing, even though mechanically it seems solid to us, right? So it has this fluid-like behavior. But let's say that an earthquake comes along. So when we talk about fluidizing soil, this is a thing that typically happens from earthquakes or from rainfall events, right? And this is that the soil is behaving like a solid to us, and then it seems to suddenly turn into a liquid and flow. But there's this kind of contradiction because I was saying, hey, even here the soil before the earthquake is flowing like a fluid. It's just doing it very slowly. But then when it gets shaken by an earthquake, it flows, but very quickly. So that fluidization is a kind of phenomenon that is distinct from this deborah number kind of argument about flow, right? And in order to understand that, let's think about the loading that comes from an earthquake. So there's a range of frequencies of seismic waves, but a good characteristic scale in the middle of that range is about 1 hertz, right? So if we wanted to put that loading time in terms of years, the loading time would be like 10 to the minus 7 years. Oh, not meters, years, right? That's a very short time scale. And so what that means is if we consider the loading that comes from shaking, we would say that the deborah number you come up with is like, from an earthquake, is like 10 to the 8. It's giant. Much, much greater than 1. So it says that the response of the soil to an earthquake should be a solid-like response, right? The loading timescale is short. The response timescale of the grains is slow, so the grains cannot respond gradually. And indeed, what happens when an earthquake occurs, I'll make this a little dashed line now. There is a solid-like response. In fact, a landslide occurs when the soil essentially fractures. And so when you shake the soil very rapidly, the soil has a brittle-like response, and it elicits the development of a crack. This is the slip surface that develops in a landslide. And you get a chunk of soil that detaches as a solid. However, the chunk of soil that detaches flows, right? So you've broken the material in a solid-like way, but what it does after being broken is a fluid-like behavior, right? And that means that the deborah number is useful, but not complete for understanding this problem, right? So the last thing we're going to do then is that we have to explain this apparent paradox that fluid-like soil that is creeping slowly creates solid-like failure that then creates a fast fluid-like flow, right? It kind of seems like it doesn't make sense. And so here's what we're going to do is right, a seismic shaking essentially has, right, is a wave like this, right? And so what we can do is we can say, all right, right, so this, of course, the wavelength is our timescale of loading, right? Or the period of the seismic wave is our timescale of loading. And you could also say that there is an amplitude, right? A total amplitude associated with this shaking. And so what we can do is to come up with a peak acceleration that is associated with this shaking, because that's the thing that gives the body force that causes fluidization, right? And that peak acceleration, we could just say, is the amplitude of the shaking divided by the loading time squared times gravity, right? So this is the peak acceleration that comes from the shaking from an earthquake. Well, the thing is that if you think about what's going on here, it's that there's a bunch of grains that are in frictional contact with each other, sitting there. And if you shake them with an acceleration that is greater than the weight of the particles, then what will happen is that they will lose their frictional contact, right? And so what you want to do is come up with some dimensionless shaking force, right, which we'll call alpha. And the dimensionless shaking force for us is basically going to be the peak acceleration that comes from the shaking divided by gravity, okay? So if you shake it larger than gravity, you've created a force that's larger than the force that's holding the grains together, and they fall apart, okay? And if alpha then is greater than 1, we're going to call that fluidized, that the soil gets fluidized, okay? So putting this together then, we have this deborah number kind of argument for something behaving like a fluid or a solid. And then we have this fluidizing problem where you shake something sufficiently and it just loses all its rigidity, right? And so we can draw this kind of phase diagram, right? And in this phase diagram, we're going to have the deborah number on the x-axis, and we're going to have this dimensionless shaking amplitude, or if you want to relate it to our other problems, you could also consider it the stress applied on a material compared to its yield stress, right? So we know that beyond a yield stress, a material will flow. We know for granular material that if we shake it larger than gravity, it's going to flow, right? So there's this number here, which is 1. This is going to be the boundary above which we are fluidized, right? And then we have this boundary right here at deborah number 1. And if we're smaller than that, we know that things are flowing. This regime, where things are flowing but not fluidized, this is the regime where the material is deforming, but it is below the critical yield stress at which it loses all of its rigidity. This regime is what we will call creep. Creep is the flowing-like behavior of solid material. It is flowing in a deborah number kind of way, but it is flowing beneath a stress at which it would lose all rigidity and flow catastrophically, right? This regime right here would be the regime that everyone would say is solid, that over the timescales of loading or observation that we care about, there's not any significant deformation. This is the solid-like regime here. One point that I want to make is that certainly the boundary between creeping and solid from a deborah number is fuzzy, right? We wouldn't ever say there's a razor-sharp number below which it's a fluid and above which is a solid. The other point that I want to make is that this boundary is fuzzy. When you have materials that are creeping and deforming, even at low stresses, when you increase the stress of those things, they transition here. The transition that happens here is more gradual than if you have a material that is not creeping over time because we care about it all, and then you apply enough stress to cause it to yield, right? And so in terms of connecting that back to this stress-strain relation that we had at the beginning, right? This transition would be materials that are brittle, right? And this transition would be materials that are ductile, okay? So to summarize what we talked about, right, the first point is everything flows if you wait long enough, and Earth can wait a long time. It's 4.57 billion years old and counting, right? The other thing, which is pretty subtle but is going to be important for us, is that there's two kinds of flow. There's flow like liquids that you and I are familiar with, which for soft Earth materials happens when you shake them or stress them enough. And then there's this creeping-like flow that happens when you're below the stress at which they're fluidized, but they still deform. The transition from creep to fluidized can be abrupt or gradual, right? And it depends on the material-controlled relaxation time. Understanding that relaxation time is fundamental, and determining it can be hard. And the thing for us is I bring all this up because we live on a soft Earth landscape, right? So we live on a landscape where the materials that we deal with are both solid and fluid-like on geologic time, and that fluidize on timescales that matter a lot to us. And so determining the nature of these transitions is actually existential. And so I've set the plate for the coming lectures, and thanks for your attention.